Welcome, ladies and gentlemen. My name is Matisse, this is Alfie, this is Lucas, and this is Amy, and we are from the Canterbury Academy in Kent. Firstly, I wanted to start off by talking about muons. Muons are high-energy leptons that decay within 2.2 microseconds and travel near to the speed of light. Muons are produced by collisions of cosmic rays in the upper atmosphere, which create a shower of muons. Here, in the upper right picture, we can see cosmic rays colliding with the upper atmosphere, which create a shower of muons, which can then be detected on Earth. On the bottom right image, this is our data that we collected ourselves that we suspect is a muon, as it's high energy. About 100 muons hit each meter square every second of Earth, and muons are higher mass versions of electrons. They are around 200 times the mass. We use the MX10 particle detector chip, as was explained before. We aim to detect muon distribution. We use shielding to remove low energy background and improve detection. We will talk about this later on in our speech. We suggest some changes to the TAPAS algorithm. It is an algorithm that identifies types of particles that were detected by the image from the chip. I will now pass over to Lucas.
So as you can see in the far left picture, muon shows up as a long, straight line. And because they come from above, we had to put the chip vertically to get a good show of lines. But because of this, we had a very small surface area that we could use to collect data from. So we had to put a long exposure time. Then, however, we would get a lot of background radiation over an hour of exposure. So we investigated different types of shielding, which you can see in the second graph. This shows our results for air, tin, galvanized, and enameled steel, which weren't great, and then the autoclave and lead, which we used later on. Mainly used the autoclave as it was the right size to hold the chip, and we found quite a lot of radiation was kept out by the autoclave. However, when we retested the chip later on this third graph, it showed that most background radiation still got through, and the reason for this, we think, is because all of the shielding that we were using is still slightly radioactive.
We then did some experiments with alpha, beta, and gamma sources to see if any of these gave an identification of protons. None of these sources generated muons or protons, and so we hope that may help us to identify what was going on. Our alpha source gave off 24.8% of protons and 17.5% gamma. We expected only beta to be present in our beta source, but unexpectedly see gamma rays that may be real, and also see protons. Our gamma source, cobalt-60, releases gamma and also beta. We saw both beta and gamma, but also saw 30.2% protons.
Whilst using the chip, we noticed that it was misidentifying muons and recording them as protons, which we know isn't possible as these subatomic particles shouldn't be present at ground level. However, we're extremely privileged to have the opportunity to reach out to Will Fennell in hopes that we could contribute our findings into resolving this issue in his impressive TAPAS algorithm. Thank you for your time and for listening to the Canterbury Academy.
For the group that just spoke, surely if you were trying to get muon count for solar activity over time, solar activity would be strongest during the day, obviously, on a bright sunny day when the sun is out. So couldn't you compare the muon count of the day versus the night?
That would be something to do. Our count was, like, the run of frames was taken for 16 hours. So that's like moved from day to night, so there shouldn't be an effect of that on our data, but it's definitely something to think about. And of course, if there is if cosmic rays are accounting for these muons as opposed to just solar activity, then possibly that has an effect.
Okay, another question? Yeah, there's one right in front of you there, Steve.
I've got a question for your group, and you said at your group here, you said your data logging system started to log your information wrong at one point. So what was that like for you as a group to know that it had been collected wrong?
Well, we think that we saw lots of straight tracks on the data, which are the tracks of muons. We know that already. And then when we looked them into the TAPAS algorithm, we saw that they were being classified as protons, which we thought was quite interesting. It didn't really, we didn't feel it was a bad thing. We just thought that that's quite interesting. So we did some further investigations into what it saw as protons. And then we didn't really have that much of an emotional effect on us. We just thought that that's quite interesting.
But you showed perseverance in finding the answer to the unknown. So I think that's very well done. Okay, let's thank our two muon groups. Thank you.